Hi, my name is Jean-Claude Clark, and in this video we will go through part 1 of the step-by-step walkthrough of the magnetically coupled resonant wireless power transmission printed spiral coil design process used in the design of our coils for cell phones. Before we continue, I must confess, that name is just way too long. Even the acronym MCR-WPT PSC design process is too much of a mouthful to say. So moving forward, we will shorten it to the MCR coil design process for the rest of this video. Alright, with that out of the way, we will continue the video. In the first half of the walkthrough, we will first establish our design specifications and then cover the momentum portion of the design process, which starts at the substrate and simulation setup and ends at the importation of the design into EMPro. So let's get right to it. We begin by establishing the specifications of the double-layer MCR coil design used for cell phones as follows. The maximum current through the source and load coils is 1.2 amps. The maximum number of outer coil turns is 10 turns. The maximum outer coil length and width are 5 inches and 2.5 inches respectively. The minimum S to 1 power transfer coefficient is negative 1.3 dB, and the frequency of operation is 6.78 MHz. To satisfy the current specification, we took into consideration the potential proximity effect resistive losses between adjacent traces on the same layer and different layers, as well as the resistance due to the skin effect. The PCB trace thickness is limited to 2 ounces of copper, which is about 3 times the skin depth of copper at our operating frequency. Using a trace width calculator based on formulas from the IP 2221 standard and entering the copper thickness and maximum current values, the minimum trace width is 19.8 mils. For our design, we used an inner coil with 1 turn and a trace width of 50 mils, which is more than twice the minimum trace width required to handle our maximum current. For the outer coil, which has 7 turns and is inductively coupled with the inner coil, the maximum current is 1/7 the inner coil maximum current. We used an outer coil trace width of 21 mils, which is much larger than the minimum trace width required using the calculator. The resulting MCR coil parameter list used in our prototype design is shown here. With our design parameters established, we now move on to the MCR coil design process walkthrough. The first thing we do in the design process is the momentum substrate and simulation setup. In our design, we used a double-layer FR4 board with a core thickness of 26.4 mils and 2 ounces of copper on both sides. Using the default momentum substrate, we updated the substrate with these values as shown. An air layer was then placed in between the PEC, ground plane, and the board to minimize the field effects that the PEC would have on the board simulation. A solder mask and sill screen are not required for the design of our prototype and were not included. Next, the simulation frequency plan was set to an adaptive simulation type with a frequency range of 0.5 to 25 MHz and a maximum of 50 steps. All of the remaining simulation setup parameters were left at their default values. With the substrate and simulation setup complete, we now begin the spiral coil creation. Using the T-Lines microstrip palette on the left-hand side, we place a microstrip rectangular inductor macro in our layout and enter the inner coil parameter values. From the Spiral Art OA example workspace, we then copy the 2-layer inductor symbol into our layout and enter the outer coil parameters. With the layout centered, we add ports to the inner coil. Now we flatten the 2-layer inductor outer coil we remove the via and adjust the inner turns of both layers such that they no longer overlap with the inner coil. With the design complete, we will take a quick look at the 3D model of the layout. Here we can see the ports, the PEC ground layer, the inner coil and outer coil, bottom copper layer, the substrate, and the outer coil top layer. With that, we have completed the spiral coil creation. And we now run the momentum RF simulation to generate the S parameter results, then do some post-simulation analysis. Looking at the S11 graph, we can see that the self-resonating frequency of the MCR coils is estimated to be about 7.3 MHz, which is within our estimated range. And the frequency versus resistance graph shows a peak resistance of about 318 ohms. Next, we do an insertion loss analysis using the peak resistance value from the graph. Since we have identical coils on the transmitting and receiving sides of the MCR coil system, both the S11 and S22 resistance values of the system are the same as the S11 momentum simulation resistance value. With the load and generator impedances matched to 50 ohms, we can run an S parameter simulation with two resistors in parallel inserted in between the 50 ohm terminations to get an estimated maximum S21 power transfer coefficient at resonance. We run the S parameter insertion loss simulation and get an estimated S21 for the MCR coils to be -1.27 dB, which meets our specifications. With the simulations complete and the specifications met, we import the design into EMPro. And with that, we complete part 1 of the step-by-step walkthrough of the MCR coil design process. Thank you for watching, and see you in the next video.